Hello, everyone. This video is for my Camden County College students. This is the last week for the videos, and today I'm going to cover 7.3 of your textbook, which is on hypothesis tests for a population mean when the population standard deviation is unknown. So that's what we're going to spend our time today on. I will go through the textbook, show you the methodology that we used last time. We're going to apply it this time with just some minor changes because of the fact that we don't know the population standard deviation. Then I'll go over 3 examples from your textbook for hypothesis tests. One which is a two-tailed test, another one which is a left-tailed test, and the third one which is a right-tailed test. So we're going to be doing 3 examples of hypothesis test in this section. Then on Thursday, we're going to complete our videos by looking at section 7.4, which is basically how to do a hypothesis test for population proportion. And that will be it for the semester in terms of new material. Then next week, I will post a sample test number 3. Probably, I'm thinking about when I should be doing it, but probably no later than Monday of next week. I will post that sample test for you, for everyone. And then later in the week, I will post the solutions, all right? So that'll be the, and then the week after that, which is on a Tuesday, is when our test number 3 is. All right, so we'll go over, I'll be sending emails to confirm all of that. So let's get started. We'll get to the, share the screen and get to the textbook. All right, let's go to our textbook. And this is 7.3, testing for the mean when population sigma, where the population standard deviation is unknown. So once again, we're going to go through our steps in terms of how to find, how to do the test. Now, in the beginning of this section here, they talk about how to find critical values. This is only needed if you are going to be doing some homework problems where they ask you to do this method. This is the rejection region method that I had mentioned before that we're not focusing so much on, only for homework. So you don't really need to find critical values when we calculate p-values. But when we use this other method, the rejection region method, then you need to, of course, find the critical values. And they show you here how to find critical values. So let's just review it quickly, because again, this is not the method that I'm going to be testing you on your test number 3. But again, for some homework problems, you may need this. So the rejection region method requires that you determine a critical value. And how do you find these critical values? Well, if it's a left-tailed test, you actually, on the left tail here, you actually plot your alpha, your probability of a type 1 error, which will be given in the problem. And then you use, in this section, because we're finding t's instead of z's, we would use inverse t to find this critical value here. So the area to the left would be the alpha, and then the degrees of freedom would be the sample size minus 1. So use inverse t, and then you get your t sub 0 here. That's your critical value. The right tail test, you would again plot your alpha to the right, and then find the critical value where the area is to the right. Now, with your inverse t, the area they ask for is always to the left. So you could either type in 1 minus alpha for the area to the left, or you could just figure out what that is and type in the number directly. And then for the two-tailed test, to find these two critical values here, you split the alpha into two equal pieces. Half of it goes to the right tail, half of it goes to the left tail. And then you use inverse t to find these two critical values here. All right, so that's how it's done using the critical rejection region method. Once again, let's just review what the rejection region method says. When you find your critical values, you calculate your test statistic. And if it's a left tail test, if your test statistic's to the left or less than the critical value, you reject the null hypothesis. If it's to the right, if it's larger than the critical value, then you don't reject it. With the right tail test, once you find your critical value, you calculate your test statistic. The test statistic is larger than the critical value. In other words, it's in this blue region here. You reject the null hypothesis. If it's less than the critical value in this beige region, you do not reject it, the null hypothesis. And then for the two-tail test, the rejection region method basically says that wherever you, so basically what it says is that if the test statistic is less than the critical value on the left here, or greater than the critical value on the right, in other words, in these blue regions, we reject the null hypothesis. And we don't reject it if the test statistic is in between these two critical values, in other words, in the beige region. All right, so that's the rejection region method. And they do give, they show you how to find the critical values in examples here and here on this page, page 378. Again, I'm not going to stress that at all, only for homework. Anyway, on this page, 379, they show you the formula for the test statistic. All right, you're going to be doing a t-test whenever you want to do a hypothesis about a population mean, and the population standard deviation is unknown. So here's the formula right here. The numerator is, it looks like the z, test statistic, x bar minus mu, x bar being the sample mean, mu being the hypothesized mean. And then your denominator looks a little different. Instead of having the standard error, instead of having sigma divided by the square root of n in your denominator, you have s, the sample standard deviation, divided by the square root of the sample size. The conditions that need to be met to actually run the t-test, again, are that the sample has to be randomly selected, and then you have to meet the central limit theorem. That is, either the population is normally distributed, therefore the sampling distribution is normally distributed, or if there's nothing being said about the population, then the sample size has to be at least 30. You do need degrees of freedom in calculating the p-value, which we're going to be doing in this section. And the degrees of freedom, again, is the sample size n minus 1. So they show you here how to come up with, now these guidelines on this page here are asking you to use the rejection region method, which we're not going to do. All right, so again, if you want to look through these steps for the rejection region method, that's fine. You know, you may again need to use it in examples for your homework, but I will not test the rejection region method. I want to make that really clear to you. It will not be tested at all. We're going to use the p-value method. So just so that we don't run into any issues, I'm going to skip these examples here with the rejection region method here. I'll go right with the p-values. This is exactly what I'll be testing you on in test number 3. All right. So we're going to get right to it. We'll do a couple of examples in this section here, starting on page 382, on how to do a hypothesis test using p-values when the hypothesis test is regarding a population mean and the population standard deviation is unknown. So we'll show you a couple of examples, and I'll show you some examples in the back of the book, and that'll be it for today. So example 6 here is a good way of starting. It says a Department of Motor Vehicles office claims that the mean wait time, and this is how long the person's waiting inside the office before they're being helped, is less than 14 minutes. All right. Random sample of 10 people has a mean wait time of 13 minutes with a standard deviation of 3.5 minutes. At alpha is equal to 0.10, test the office's claim. All right, now, the claim, if you read the claim again, it has the word less than in it, or the phrase less than 14 minutes. Less than is a phrase that's used in the alternative hypothesis. Remember, the null hypothesis only has equal signs in it. Either it'll have an equal in it, the null hypothesis, or less than or equal to, or greater than or equal to. The alternative hypothesis will have not equal to, or less than or greater than. In this case, it's less than. So this claim is the alternative hypothesis, and you can see it down here. Mu, because it's a population parameter, we're using mu, is less than 14 minutes, is our alternative hypothesis. The null hypothesis has to be the complement of less than, which is greater than or equal to. So that's why the null hypothesis states that mu is greater than or equal to 14 minutes. All right, now the X bar, the sample mean out of a sample of 10 people, is 13. And it says with a standard deviation 3.5 minutes. Now, how do you know whether that's the population standard deviation or the sample standard deviation? Well, if it was the population standard deviation, they would state population standard deviation. Since they have not stated that population standard deviation, and they mention it in the same sentence as a random sample of 10 people, and this standard deviation is the sample standard deviation, not the population standard deviation. It's S. All right. So that means we're going to be doing a t-test, not a z-test. All right. Alpha, which is the probability of a type 1 error, we also call it the level of significance, is 0.10 or 10%. All right. It says assume the population is normally distributed. That's because the sample size is less than 30. All right. The sample size was at least 30, we wouldn't have to worry about whether the population parameter is normally distributed or not. But because the sample size is less than 30, we do need to know it, because if it's not normally distributed, we can't do the t-test. But it says here it is normally distributed. So we're good. So here's the solution. Well, here's our step number 1 is to state the null and alternative hypotheses. We know that the alternative hypothesis is the claim. All right. And even shows you here, by the way, it shows you could go into t-tests in your calculator directly into t-tests to come up with your solution. What I have found from my own experience, and this is important, my own experience of teaching this course several years, is that students tend to get confused about which selection they should choose whenever they run into a problem. And they often pick the wrong test and then end up with the wrong answer. So the best thing to do is follow the steps that I give you, which is a little bit longer, but it's doable, and you can always get the right answer. So if you want to learn these tests on your own and if you feel like you're good at them, be my guest. I will not teach you these tests because they, again, students tend to make lots of errors when using them. So I tend to avoid the calculator. So these things that are mentioned in the calculator, I will not use. However, what I will do in this case here is show you with the calculator how to come up with the answers. Now, one thing that's important to know is step number 1 is stating the null and alternative hypothesis. Step number 2 is determine whether we can use the normal distribution for a sampling distribution. And the answer is yes, because the population distribution is normal, like it says up here. All right, so we're good with that. Step number 3 is to calculate the test statistic. Now, the test statistic is that formula. It's going to be that formula that we saw on, let's see if I have this here. It doesn't show you on this page, but we saw it earlier. Let's look at it once again. Let's just go back and find that formula. Here it is in this problem here. It's T is equal to X bar minus mu divided by the S divided by the square root of N. So we're going to do that in this case here. And remember that X bar in this case here is equal to 13, and S is equal to 3.5. All right. Mu, the hypothesized mean, is 14, because that's what's stated in the null and alternative hypotheses. So what we're going to do is go to our calculator, and I'm going to open up a set of parentheses. I'm going to calculate the test statistic, the T statistic. So X bar minus mu is going to be 13 minus 14. X bar is, all right, X bar is 13, mu, the hypothesized value is 14. We're going to close parentheses, and we're going to divide by, and notice again, I have to use parentheses both for the numerator and denominator. The denominator is S, which is 3.5, that's our sample standard deviation, divided by the square root. Follow these steps. And what is the sample size again? So you need to go back to the problem. Go back to the problem. The sample size is 10, right? Sample size is 10. Let's go back to our calculator. We're going to put the square root of 10 here as in our part of the standard error formula here, 3.5 divided by the square root of 10. Now, notice that it's blinking inside the square root. To get it outside the square root and close the parentheses, I need to hit the right arrow key again, close parentheses. Now, if I hit enter, this should be our test statistic. Now, let's go back to the problem. Notice that if we scroll down, there's our test statistic right here, negative 0.9035. All right, so there it is. So it's easily done, and this is the way I would like for you to do it, instead of using finding this t-test and all of that sort of thing. I want you to go through these steps. That way you know you're going to get the right answer each and every time. Now, here's the thing. This is our test statistic, right? Now, if we're going to use the p-value method, how do we know which test that we should use? Is it a left tail test, right tail test, or two tail test? Well, if we go back, we always look, here's the key, we always look at the alternative hypothesis. And we look at the direction of our operation here. It says less than. Notice it's pointing to the left. It's pointing to the left tail. This is a left tail test. When we have less than in the alternative hypothesis, this is a left tail test. All right. So what we need to find is the probability that T is less than what? Is less than that test statistic. This here, this number here. Here's our test statistic. We want to find the probability that T is less than that, and that's called the p-value. Now, how do we find that? Well, remember, with probabilities, and we're going to be using T here as our statistic, we must use T CDF. So I'm going to hit second, and distribution, and everybody's calculator, including the people who have the 83 calculators, everybody has the TCDF. So you choose that, hit enter. And now, here's one thing that we did not do, and let's go back, actually. I want to do one more step here. Notice this T statistic is very long, has lots of digits. You could round it if you wanted to. One way of doing this problem to make it a little easier is to store this number into an alpha character like T. I've shown this to you before. So if you hit this store button right here, STO, all right, and actually it looks like it doesn't recognize anymore this negative 9.035. So you usually have ANS here showing that it's taking this number here, but it doesn't have ANS here. So what I'm going to do is enter this number again. I'm going to hit enter again, just to repeat this process here. And now, if I hit the store button, notice it has ANS, which means answer. It's the previous answer. It's the previous number that was answered. I want to store that into T, the letter T, which is right above the 4 here, and then hit enter. Now, the reason I did this is that way I don't have to, I can use the full number here instead of having to round it at this point when I do my TCDF. So this test statistic is now stored in the letter T. Now what I'm going to do is go to TCDF, hit enter. And now I need to find the probability that at my T, small t, that the T is less than this negative number. So less than means my lower limit will be negative 1,000. Now my upper limit now will be that negative 0.9035, but I've stored it into the letter T. It's just a coincidence it's called T in this case here. I could have used any other letter to store it in. I could have stored it in A or B. I used T, so I'm going to hit second alpha 4 here for T. Oh, I made a mistake there. Let's clear that out. I didn't use alpha, I used second. That's important here, you don't make that error. So you're going to use alpha here to find that letter T. Here we go. All right. Now, degrees of freedom is the sample size minus 1. And remember, the sample size is 10. So I'm going to put 9 here. And I'm going to scroll down and hit enter. And hit enter again. And this is my p-value. That's the probability that T is less than that negative 9.035, this number here. And notice it's 0.194 and a bunch of numbers after that. It might make sense to round this to 3 decimal places. 0.195 is my p-value. So in case I asked you that question on the test, that's the answer. Actually, if you go back to the book, actually they rounded the p-value here to 0.1949. All right, so that's what I got with my calculator here, 0.1949. All right. So now I have my p-value. Now, what does the test, the t-test say to do? What you're going to do is compare this p-value of 0.1949 to the alpha. And what was alpha again? The probability of a type 1 error. Well, let's go back to it. Alpha is 0.10. Well, the p-value of 0.1949 is larger than 0.10. What's the decision rule say? Well, if the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. In this case, the p-value is 0.1949. That's bigger than 0.10. So we do not reject the null hypothesis. That's the conclusion here. All right. So it says it right here. And since the claim is the alternative hypothesis, notice how they write the interpretation. Number one, they'll say there's not enough evidence at the 10% level of significance to support the office's claim that the mean wait time is less than 14 minutes. Well, this is the same thing as rejecting the null hypothesis, but the claim happens to be the alternative hypothesis. So when you reject the null hypothesis, you are supporting the alternative hypothesis, which happens to be the claim. So that's why they state it in this way here. Instead of saying reject the null, they're saying support the claim, which happens to be the alternative. So there's not enough evidence to support the claim that the wait time is less than 14 minutes, okay? There wasn't enough evidence because the p-value is too big. It's too big relative to the alpha. All right? All right, so let's actually do another one. That's a left tail test. Oops, they don't have another one. So that's how to do one of these tests. Now, One thing we could do actually is do the one that's down here. Let's see, let's take a look at that. Well, here's a good example right here. So let's take a look at try it yourself, number 6. And I hope you have a pencil and paper with you so you can jot down this information. It says another Department of Motor Vehicles office claims that the mean wait time is at most 18 minutes. Notice that term, at most. Now remember, when we first started hypothesis tests in 7.1, I believe on the very first page, or the second page, I forget which page, but one of the first 2 pages, it had a list of all these phrases like at most or no more than, phrases like that. And we translated that into symbols, remember? So if you go back to 7.1, if you're not sure about this, when it says at most, that means less than or equal to, at most. So less than or equal to, it has that equal to in it. That must be the null hypothesis that they're having the claim in this time. All right. Previous problem, remember, was the alternative hypothesis was the claim. All right. So we'll get to that in a second. It says a random sample of 12 people has a mean wait time of 15 minutes with a standard deviation of 2.2 minutes. And now the level of significance is 0.05. So we need to test the opposite claim. So the null hypothesis, I'm going to write this down in a second, is that mu is less than or equal to 18, because it says at most. At most means less than or equal to, which means the alternative is mu is greater than 18. So let's actually, let's see here, 1 second. Let's see if I can find the whiteboard here. So I'm going to stop the share on this temporarily. Go back to share screen and let's go to the whiteboard. Let's actually write all this down. All right, so let me show you the whiteboard. And so what we're going to do is I'll do the text here, the text box. And I'm going to write the null and alternative hypothesis. So the null hypothesis is going to be, let's say H, and I'll put a little O here next to it. And instead of writing the Greek letter mu here, I'm just going to type in mu. All right, so mu, it's going to be less than or equal to. All right, so instead of putting less than or equal to, I'm going to write it this way, less than or equal to 18. That's going to be our null hypothesis, because that means at most, less than or equal to. So that's going to be our claim. So I'm going to write claim here. Claim is going to be the null hypothesis. And then the alternative hypothesis is going to be mu is greater than 18. Greater than 18. All right. So that would be step number 1. This would be our null and alternative hypothesis. Mu less than or equal to 18 is our null hypothesis, which is the claim, at most 18. And therefore, the alternative would be mu is greater than 18. All right. So that would be the null and alternative hypotheses. All right. So I hope everybody is clear about that. So let's go back to problem. All right. So the problem, all right, is stating that the X bar, for a sample of 12 people, the mean wait time, which is X bar, is 15 minutes. All right. So again, let's go back to screen here, and I'm going to say X bar. All right. Hopefully you know that that's what it is going to be equal to, and once again, let's go back and see what it says again about X bar. 15 is X bar. So X bar is 15. So let's do that. Sorry about that. Just give me a second here. This is equal to 15. And what else do we know? We know that the sample standard deviation is 2.2. 2.2. All right. So that's our information. And the sample size, I guess we need to write that down, is 12. All right. So that's all of the information from the problem. Now, one thing that you need to notice from all of this is that the alternative hypothesis, even though the claim says less than or equal to 18, the alternative hypothesis, which is the complement of the null hypothesis, says greater than 18. Greater than 18 is going to indicate a right tail test. All right. So don't be fooled by the problem because it says less than or equal to. The alternative hypothesis is greater than. That's a right tail test. That's what we're going to be doing. All right. Now, what we're going to be doing is calculating our test statistic, which remember again is x bar minus mu in the numerator, and the denominator is going to be s divided by the square root of the sample size. So we have everything here that we need, right? Because x bar, remember, is 15. All right. X bar is 15. Mu is 18. And here's s and n. So let's go back to the problem. All right, let's go back here. All right, so let's just read through it again. All right, now notice in this case here that the x bar is actually less than 18, which is a little bit strange that it would do that. But that's what we ended up with. All right, so I think you're going to see that the answer is going to be that we're not going to reject the null hypothesis in this case here, but let's look at it anyway. All right. So what we're going to do next is we're going to calculate with our calculator we'll just clear this out here, our test statistic. So x bar is 15 minus the hypothesized mean of 18, close parentheses, divided by our standard error, which is going to be s, which is 2.2, divided by the square root of the sample size. The square root of the sample size is 12. Once again, I'll hit the right arrow button here, close parentheses, and hit enter. Oops, looks like I made an error. So let's go back. Let's hit one here and go back. What mistake did I do here? I said 15 minus 18 divided by 2.2 divided by the square root of 12. Okay, so something is not right here. I don't know why this is giving me an error. Let's do it again. All right, so we're going to do 15 minus 18. Maybe I'm a little sleepy right now. Divided by, and then in parentheses, I'll put 2.2 divided by square root of, oh, no, I'm all right, square root of 12. All right, so I think I did everything right there. It looks exactly what oh, I see what I did before. All right, this is a common error. Notice up here, I use this as the minus sign. This is the negative sign, right? What we put before numbers. And it's not the minus sign. This is the minus sign. So there's my error. All right, so lucky me, I figured it out. All right, there is our test statistic, our t, negative 4.723. Now, again, I'm going to store it in my calculator. Again, I'm going to use t by storing. Remember, if you store a number and something else was in there before, this will just replace it. So if I hit enter, this number is now in t. Now, because this is a right-tail test, I want to find the probability that t is greater than negative 4.72. So how do I do that? Again, I use TCDF because it's a t that I'm looking at here. Go down to TCDF, hit enter. And because it's a greater than problem, I'm finding the area to the right of that number. I need to put the t here as the lower limit. And then the upper limit becomes a positive 1,000. You've all done this before. Our degrees of freedom is one less than the sample size of 12, which is 11. And I scroll down, hit enter. And this should be a pretty large p-value. Yeah. This is an unusual problem. I don't know if the people who created the textbook made a mistake here in creating this problem, but this is the answer, actually. The p-value is very large, and it wouldn't even matter what alpha is. We will not reject the null hypothesis, all right? The sample actually gave us a number less than the hypothesized value, and the test is actually saying greater than. That's the alternative hypothesis is saying greater than. So this is a case where we would not reject the claim. The claim in this case is the null hypothesis. We would not reject the claim that is less than or equal to 18 because we end up with a sample that actually said 15. So, so here's an example of p-value that's very large. All right. So anyway, don't worry about that so much. Let's now go to our end of the textbook. Let's actually do some examples, which are better examples than this one. All right, so I wouldn't pay so much attention to this example. And by the way, I'm just going to clear this out. Go back to the textbook. And let's just go to this section here. And we're going to go to actually page 384. All right, 384. And we're going to look at number 19. All right, now I do have solutions for these, so don't worry about it. Now, in this particular section here, they're saying hypothesis testing using rejection regions. Well, I did not go through these steps here. I'm using p-values. Remember, that's the way I would like for you to calculate these. And in your test, which will be multiple choice, we'll be asking you to find p-values. So ignore this here. We're going to go through those 6 steps I showed you last time for doing hypothesis tests. And I'm going to do them using the same 6 steps this time. So let's read through number 19. A used car dealer says that the mean price or the average price of a 3-year-old sport utility vehicle, which is in good condition, is $20,000. You suspect this claim is incorrect, all right, and find that a random sample of 22 similar vehicles has a mean price of $20,640 and a standard deviation of 1990. So this is the sample mean, this is the sample standard deviation. Is there enough evidence to reject the claim at alpha is equal to 0.05? So let's read through it again. A used car dealer says that the mean price of a 3-year-old car is 20,000. Is means equal to. Equal to, where's that? Which hypothesis? Yeah, that's right. It's the null hypothesis. That's where the equal to is. So that means the alternative hypothesis is going to be not equal to. That's the complement of equal to. All right. So let's go back to our, see if I still have the share. There we go. So what I'm going to do is erase that. Let's just erase all of this. There we go. Go back to create another text box here. And so let's look at the problem. So let's look at the problem again. The null hypothesis is that mu is equal to 20,000, and the alternative is mu is not equal to 20,000. So again, here's our, so we're going to say h sub 0, and we're going to say mu, right, is equal to 20,000. The alternative is going to be mu is not equal to. So I'm going to say not equal to, all right? All right, and that's our null and alternative hypothesis. So immediately in the alternative hypothesis, we're going to look at it and say, oh, we're going to do a two-tailed test because that's not equal to. All right. All right. So the claim, now this here, the null hypothesis is the claim, and the alternative hypothesis is not the claim. All right. All right. Anyway, let's go look at the solution. Once again, sample size 22. 20,640 is the sample average, the sample mean for the 22 vehicles. And the sample standard deviation is 1,990. Here's our level of significance, 5%. So step one here, again, is our null and alternative hypothesis, like I just typed. Step number two is, can we do the test? Is the sampling distribution normal? Well, it says here n is 22, that's less than 30, but it must say somewhere in this problem about the population being normally distributed. Well, it does up here. See it up here in the heading. Assume the population is normally distributed. We're good. All right, so we can do the test. All right, so let's go back. Step number 3 is, it says sigma is unknown. The only thing that they give you is that the sample standard deviation is 1990. Remember, the only way it's a population standard deviation, and the problem is that they say population standard deviation. If they don't use the word population, you need to know that that standard deviation is the sample standard deviation, right? So therefore, we're going to use the t statistic instead of z statistic. Again, here's the formula for a test statistic for a mean, but instead of using sigma in the denominator, we're using s for the standard deviation. The numerator looks the same, x bar minus mu. Denominator in this case is s divided by the square root of n. So the numerator is 20,640, and I think I made a little error here. Notice I have 2,000 here. It should say 20,000. I'm going to have to make a correction when I post this. So just know that there should be another 0 right here. Right here should be 0. So our test statistic should be 20,640 minus 20,000, not 2,000, divided by s, which is 1990, divided by the square root of 22. And this ends up being 1.5085 as our test statistic. All right. So actually, let's show it with the calculator since I did not write this down correctly. 1990 and 22. Let's actually use our calculator and verify that we did this calculation correctly. So we're going to open up a set of parentheses. Again, we're doing our test statistic. And the sample mean is 20,640 minus our hypothesized mean. Notice I have 20,000 now in here, divided by, again, parentheses, the sample standard deviation, 1990, divided by the square root of the sample size, which is 22. Again, hit my right arrow button to take the cursor out, close the parentheses, hit enter, and there it is. All right, so I just verified that is the correct test statistic. Now, if I was going to do this problem, what do? I can store this, right? Makes it easier. So I'm going to store this number. And again, I'm going to use t, alpha 4, alpha t. And this number now is stored in t. All right, replace what was in t before with this new number. This is my test statistic. Now, let's go back to whiteboard here. Since this alternative hypothesis says not equal to, this will be a two-tailed test, right? A two-tailed test means the following, and we're going to look at this problem a little bit over here. What it means is that the p-value is going to be, has two tails to it, all right? And the test statistic is positive. It's a positive t-value, so it's over here. And that means the negative of 1.5085 is over on the left side here. Half the p-values to the right, half the p-values to the left. So when I find the probability that t is greater than this number, this is the right tail test, remember. This is similar to a right tail test because we're finding the area in the right tail here. It's not a right tail test, it's a two tail test, but because the t statistic is positive, we're going to calculate it like it's a right tail test. But we should just know that when we calculate this probability here, that t is greater than 1.5085, this is 1/2 the p-value. It's just 1/2 of the answer, all right? So how do we translate this to, with our calculator? It's t-CDF. Because it's greater than, we would say 1.5085, or in the case that I'm doing here, we can simply put t in there, right? And I'm going to put t in t-CDF because I stored it there, didn't I? I stored that t statistic there, so I'm good. I don't have to remember the number or write down all the digits. Now the degrees of freedom, it's 22 is the sample size. I'm going to put 21 here. Scroll down and hit enter. And there is my 1/2 the p-value. It's not the full p-value, it's 1/2 of it, 0.073. Let's go back to here. Here it is. This is the number we just got. See it? 0.0731657. I think I wrote all those digits down. Now, with a two-tailed test, whatever area that you find, because it's only 1/2 the p-value, you need to multiply it by 2 to get the full p-value. So 2 times this number here is 0.1463, right? And that's just the sum of these two areas here. All right, that's my true p-value. Now, since the level of significance is 0.05, alpha is 0.05, and the p-value is 0.1463, since the p-value is greater than alpha, our decision rule is do not reject the null hypothesis. Okay, do not reject the null hypothesis. Now, let's look at step 6, which is the interpretation. It says at the 5% level of significance, there is not enough evidence, because we didn't reject the null, to reject the claim. Remember, the claim is the null hypothesis, right? The claim, let's go back. It's 20,000 here, is 20,000, that's the claim. So since we're not rejecting the null hypothesis, we could say not rejecting the claim, because the claim is the null hypothesis. So there is not enough evidence to reject the claim that the mean price of a 3-year-old sport utility vehicle in good condition is $20,000. So those are the 6 steps, all right? Let's review the 6 steps again. We know it again. State the null and alternative hypothesis. You know, you can also write what the claim is in this case here. Step 2, make sure that we can run the test. That is, the sampling distribution that we're going to use is normal. Well, since the test is about a mean, we would check to see if the sample size is at least 30. That's the central limit theorem. Well, it's not, it's 22. However, the population is normal, which automatically makes the sampling distribution normal. So it doesn't matter that the sample size is less than 30, we're okay. Step 3, calculate the test statistic. That's what we did. Step 4, look at the alternative hypothesis. If it says not equal to in this case, we're going to use a two-tailed test. Now, why is that important? Because when we calculate, when we plot the test statistic on the t-curve, if it's positive, it's going to be on the right. If it was negative, it would be on the left. But since it's positive, we're finding the area to the right of it. But since it's a two-tailed test, this area here is only 1/2 the p-value, not the full p-value. That's because it's a two-tailed test. Once we calculate this area to be 0.073, we multiply it by 2 to get the full p-value, 0.1463. Since in step 5 says since that p-value is larger than alpha, we do not reject the null. And then we just write the interpretation. So those are the steps. All right, let's do another example, number 20 on the same page. Back to the text. Number 20, DMV wait times. Oh, this sounds familiar. This is something we were doing before. A State Department of Transportation claims that the mean wait time for various services at the different locations is at most 6 minutes. At most. Remember, we did a problem just like this. At most means what? Less than or equal to. Has that equal to in it, that means null hypothesis, all right? So at most, less than or equal to. A random sample 34 services at different locations has a mean wait time of 10.3 minutes and a standard deviation of 8 minutes. Is there enough evidence to reject the claim that alpha is equal to 0.01? All right, so let's go to the solution. Step number, here's all the data, right? No information about the population standard deviation. It only mentions the standard deviation of the sample. Sample size is 34. Sample mean is 10.3. Sample standard deviation is 8.0. Alpha is 0.01, 1%. Here's the hypothesis. It's very important to get the hypotheses right, otherwise the whole thing doesn't turn out very well. So the claim says at most means less than or equal to. Here's my equal to in here. This is the null hypothesis. The claim is all about the null hypothesis. Mu is less than or equal to 6. The complement of that is the alternative hypothesis, which is mu is greater than 6. Step 2, can we do the test? Yes, we can, because the sample size 34 is greater than 30. The sampling distribution of sample means is normal. Okay. Step 3, since the population standard deviation is unknown, we're going to use the t-test again. And here's our formula right here. X bar minus mu in the numerator, S divided by the square root of n in the denominator. The sample mean is 10.3, right? The hypothesized mean is 6, so it's 10.3 minus 6. And the denominator is 8, the sample standard deviation, divided by the square root of 34. Remember, if you do this with your calculator, remember to put parentheses around the numerator. And you end up with 3.1341 as your test statistic. Step 4, we're going to calculate a p-value. Now, in this case here, because this is if we look at the alternative hypothesis, we always look at the alternative hypothesis to determine the type of test. It says greater than, that means right tail test. Right tail test, pointing to the right. Okay. So since the alternative hypothesis says that mu is greater than 6, we're going to use the right tail test. Since this is not a two-tail test, this area here that we're going to find is the p-value, the entire p-value. The probability that t is greater than the test statistic of 3.1341. Again, we're going to use t-CDF since it's a t-test. We're going to put the lower limit, since it's greater than, we're going to put the lower limit as our test statistic. Again, 1,000 for our upper limit. And our degrees of freedom is the sample size 34 minus 1, which is 33. We end up with a p-value of 0.0018. In this case, since the p-value 0.0018 is less than alpha, which is 0.01, we're going to reject the null hypothesis. And step 6 says, is our interpretation. At the 1% level of significance, there is enough evidence to reject the claim, and the claim remembers in the null hypothesis that the mean wait time for services by the DOT is at most 6 minutes. So we're going to reject that claim. All right. P-value is much less than alpha. All right, and the final one we're going to do is on the next page, 385. So let's get back to our textbook. And then the next page. And the next page is going to be number 29, class size. All right. Let's read through it. You receive a brochure from a large university. The brochure indicates that the mean class size for full-time faculty is fewer than 32 students. Now, fewer than means less than. Less than is alternative hypothesis. So we have less than here as our alternative hypothesis. Think left tail test, right? Okay. You want to test this claim. You randomly select 18 classes. Now, 18 is less than 30, but if you look above here in these sets of problems here, it says assume the population is normally distributed. So again, it doesn't matter that n is less than 30. It's 18 in this case, so we're good. So you randomly select 18 classes taught by full-time faculty and determine the class size of each. And the results are shown in the table. Oh, all right. So the the numbers here, the 18 different class sizes here, are indicated in this box here. So no indication of sample mean and sample standard deviation, nothing about population standard deviation. So your job now is to take these numbers here and enter them as a list under stat, and then go to one variable statistics and look up X bar and S. All right, so we'll do that in a second. So the results are shown at alpha's 0.05. Can you support the university's claim? All right, that it's fewer than 32 students. So let's actually go to our write-up on this one. So n is 18. But then we have to enter data, right? That's what we have to do to get our X bar and S. So let's actually go to our calculator. And I've already entered, let's clear this out. I've already entered into L1 those 18 numbers. So once again, I go now to one variable statistics. Already defaulting to L1, that's where my numbers are. If it's in another list, you have to, of course, change that. Go down to calculate, hit enter. And here in the first number here, 30.1666, a bunch of sixes. So I actually said 30.1667, rounding it to 4 decimal places. That's our sample mean. And our sample standard deviation is S, 4.00367, that number there. So I'm going to round it to 4.0037 as my standard deviation, sample standard deviation. So now let's go back to the write-up. And here's the X bar and S. That's where I got it from. Step 1, I'm going to state the null and alternative hypothesis. Remember, the claim says, this university claims that their full-time professors on average have fewer than 32 students. That's less than, and that's the alternative hypothesis. So our null hypothesis must be the complement of that greater than or equal to 32. Step 2, of course, we know the population is normal, sampling distribution is automatically normal. It doesn't matter that the sample size is less than 30. Step 3, since sigma is unknown, we should use the t-test once again. Again, this formula for the t-test. We're going to plug in X bar 30.1667 minus 32, which is our hypothesized mean, population mean, divided by S, 4.0037, divided by the square root of the sample size, which is 18. Remember to put parentheses again around the numerator, and you get negative 1.9427 as our test statistic. Now, because the alternative hypothesis has less than, this is going to be a left tail test, right? That's what step number 4 is saying here. And therefore, the area to the left of this test statistic, because it's negative, it's to the left of 0. This area here is going to be our p-value. So the p-value is probability that t is less than the test statistic, negative 1.9427. And that is TCDF, again, because it's less than, and looks like I wrote this down incorrectly. I have to change this also. This is not correct either, all right? This is not correct either. This should say negative 1,000 on the lower end point And upper endpoint should say negative 1.9427, and this should say 17. So excuse me, this is not correct. Let's actually do this with our calculator. All right, so actually I'm going to do this whole thing. I'm going to write down x bar 30.1667. S is equal to 4.0037, and mu is 32, and n is 18. Actually, I'm going to do this with it since I made this mistake here. So I'm going to, when I post this, I'm going to obviously correct this for you. This should not be this here. This is not correct. It should have negative 1,000 for the first number here, and then for the upper limit, it should say negative 1.9427. So let's go to our calculator and actually do this problem. So anyway, we got this information. Now what do? We're going to second quit to get back to our main screen. We're going to calculate our test statistic. I'm actually going to go ahead and do this. 30.1667 minus, now what's our hypothesized mean? 32 divided by, open up a set of parentheses, our sample mean is 4.0037 divided by the square roots of what? 18. Oops, I made a mistake again. So I'm going to actually move over one here and delete that. I need to actually hit the right arrow button to move my cursor to the right and then close parentheses. There we go. Hit enter. And there's my test statistic, negative 1.94. I'm going to store it in alpha t. Now, what am I going to do? I'm going to do a left tail test. So I'm going to use, again, TCDF. Now, because it's less than, my lower limit should be negative 1,000. This is a mistake I made on the PDF that I was showing you, so I'll correct that. The upper limit, again, will be T. Degrees of freedom, what is that? Well, that's n minus 1. N in this case is 18, minus 1 is 17. Scroll down, hit enter. And there is my p-value, 0.0344. Just make sure we did it correctly here. Yeah, we did. I just wrote this down wrong. TCDF, so p-value is correct. Now, since the p-value is less than alpha, we're going to reject the null hypothesis. And remember, in this case, the claim is the alternative hypothesis. So let's see how it's written up, the interpretation. At the 5% significance level, there is enough evidence, and notice I say here, to support the claim. Why do I say that? Because the claim is the alternative hypothesis. If I'm rejecting the null hypothesis, and the claim is the alternative hypothesis, when I reject the null, I'm supporting the alternative, which is the claim. So that's why I'm saying there is enough evidence to support the claim that the mean class size for full-time faculty is fewer than 32 students. All right. So that is it for today. I showed you a two-tail test, a right tail test, and a left tail test, and using the p-value method. This is the preferred method that you'll be using for most of the problems for your homework and for your test. But again, if they do show the rejection region method, if they want you to do that, there is a section in 7.3 that shows you how to do it. But I will not test you on the rejection region method. All right. So that's it for today. And Thursday will be the final video, which will be on 7.4, which is hypothesis test for population proportions. That will end all the material for this course. So that's it for today. I will post homework later. After I post this video, I will post this video plus the PDF after I've corrected it. And I also will post homework for 7.3, which will be due again on Friday, May the 8th, which is the final deadline for all homework. All right. So that's it for today, and have a good evening. All right. See you soon.